Section 2.3. The precise definition of a limit. As a motivation, let's consider this example from your book. Example 1. Consider the function y equals 2x minus 1 near x of 0 equal to 4. And from our section 2.2, where we discussed all the limit laws, this is just taking the limit of 2x minus 1 as x approaches 4. By substitution, we just write 2x, which is 2 times 4 minus 1 equals 7, right? However, how close to our x of 0 equal to 4 does x have to be so that the y value differs from 7 by, say, less than 2 units? Okay, let's look at the graph of y equals 2x minus 1. Notice that if we let our y differ from 7 by 2 units, we create a horizontal road right here that covers this part of the graph. And consequently, what happens is that for which these values are within this horizontal strip, we have created a vertical strip around x of 0 equal to 4. And one thing that we have to notice too is that x of 0 equal to 4 or x equal to x of 0 equal to 4 doesn't have to be defined there, the y value. Okay, we're concerned about all the y values surrounding L equal to 7, our limit point. So there, we have created, like I said, a horizontal road strip centered at y equal to 7. And the cause of that is we have also created a vertical strip centered around x equal to 4 there, and see that if we keep our x's within 1 unit away from 4, that will guarantee that our y values will be within 2 units away from 7. Now what happens if we decide to if we move farther, too far away from x of 4, like more than 1 unit? X of 0 equal to 4. If we move away from x of 0 equal to 4 by more than 1 unit, like that. And notice what happens here is that, let us look at a particular x. If I pull out this x, if I get this x, where's the y value? Right there. If I get this x right here, where's the value of y? It's right here. When we widen this distance away from our x of 0 equal to 4, that means it will widen the horizontal strip right there. See, we should keep our x's within 1 unit, okay, in order that this y values will stay within the horizontal strip that is shaded yellow. Now, how do we do that algebraically to guarantee that if we keep our x's 1 unit away from 4, that will make our y values within 2 units of our limit point? Go back to the example. In order to find our solution, we want to find out for what values of x is the absolute value of f of x minus L less than 2. So our f of x is y and L is 7. So to find the answer, we first express our absolute value in terms of x. The absolute value of y minus 7, simply the absolute value of 2x minus 1 minus 7, which will give us absolute value 2x minus 8. The next thing is for what values of x satisfy this inequality. Okay, so we already have gotten that part, and we just expand this inequality. Now recall from algebra that if I have the absolute value of x less than a, this is equivalent to x between minus a and a. So let's rewrite that in this form. So what we have will be 2x minus 8 less than 2 is equivalent to 2x minus 8 between 2 and negative 2. Let's add 8 throughout so that what's left here is just 2x is between 6 here. So that means that 2x is between 6 and 10. Okay? Dividing through by 2 would mean that x is between 3 and 5. So if we let our x's fall between 3 and 5, then this inequality will hold. That is why x minus 4 is between 1 and -1. And this is the same as saying absolute value of x minus 4 is less than 1. So if we keep our x's 1 unit away from x of 0 equal to 4, then we can guarantee that the y values that differ from 7, these y values differ from 7 within 2 units. Let us go ahead and use the formal definition of a limit. Let f of x be defined in an open interval about x of 0, except possibly x of 0 itself. Remember, we've been talking about the limit of f of x as x approaches 0, which is the number L, but all we say is that as long as the x's get closer to x of 0, the corresponding f of x's get closer to L. We will now use the formal definition. So the limit of f of x as x approaches x of 0 is equal to L if for every epsilon greater than 0 there exists a corresponding delta greater than 0 such that for all x that satisfy this inequality, then the absolute value of f of x minus L is less than epsilon. Let's take, for example, this function. Okay, let y be equal to f of x. And suppose, and again, here we let epsilon be equal to 1 over 10. So that within the horizontal strip for which we get a distance away from L by epsilon, we may be able to find a delta such that if I get that delta to be the distance away from x of 0, I will create a vertical strip so that for all x's within this vertical strip, I go up and I still see that all the y values around here are within 1/10 away from L. Suppose we change epsilon. Okay, let's make epsilon. Let's take epsilon to be equal to 1 over 100. Okay, so if our epsilon is 1 over 100, then that means we will have to find a different delta. So our epsilon is 1 over 100. So we have created a horizontal strip, and then we go down and take an interval right here for which this is true, for which they are away from, the y values are away from L by a distance of 1 over 100. Then we again create a vertical strip right here such that it stays within the box here, the intersection of the horizontal and the vertical strip. The box stays within the horizontal yellow strip. And we're going to have a new value for delta depending on the epsilon equal to 1 over 100. Okay? Well, let's go even further. Suppose it's 1 over 1,000. 1 over 1,000 for our epsilon. Then again, we do the same thing. Okay, so we've got that horizontal strip. We go down and get an interval that contains x of 0. And then we get the minimum distance so that we can have an even distance away from x of 0. That's going to be your delta right there. Okay, all the way only up to here. There. Keep going further. Suppose we have an even smaller epsilon. So if our epsilon is 1 over 100,000, then we're going to have to find a delta that will match up so that all those y values will stay within the horizontal strip. So the important thing to note to notice here is that delta depends on epsilon. So it's like delta is a function of epsilon. And this is just to show how whatever we define for the epsilon, we will have to get a delta to match up for the epsilon that's given.